All right, let's dive straight into the true engineering and mathematical logistics behind the ancient world's ultimate architectural case study. Today, we're basically putting on our hard hats to look at the Great Pyramid of Giza not as some mystical artifact, but as an absolute masterpiece of human infrastructure and project management. Think of this as a masterclass for engineering students on ancient architectural logic.
Now, what pops into your head when you picture the Great Pyramid? If you're imagining a mystical tomb standing completely alone in an isolated, endless desert built by millions of enslaved laborers straining under a whip, yeah, it's time to totally clear your mind of those Hollywood tropes. While it's certainly tied to complex Egyptian afterlife beliefs and burial customs, physically, it's a triumph of hard engineering. The reality is far more sophisticated and honestly, way more fascinating. To set a clean slate for this explainer, let's contrast the popular myths against the hard realities. First off, it wasn't the first pyramid. The Great Pyramid evolved logically from earlier structures, starting with Djoser's step pyramid and the transitional bent pyramid. And you could forget the endless desolate sands. Today, the modern city lights of Giza glow right up against its base. Most importantly, it was built by a highly organized, well-fed workforce of skilled professionals. Absolutely not nameless slaves.
So here is our architectural syllabus for today. First, shattering the pyramid myths. Second, the ultimate math problem. Third, evaluating the ramp models. Fourth, the internal spiral solution. And finally, the human infrastructure. Let's get to it.
Section 1. Shattering the Pyramid Myths. Let's start by tearing down some of the most pervasive myths about the physical reality and structural loads of the pyramid, specifically regarding its true shape and size.
Did you know the Great Pyramid actually has 8 sides, not 4? It's a mathematically staggering design secret. The concavity of the faces is so incredibly subtle that it's practically invisible from the ground. It can only really be seen from the air, specifically at dawn or sunset during the spring and autumn equinoxes, when the sun casts shadows that reveal all 8 faces. It's a massive testament to their geometric precision, allowing the entire pyramid to function as a giant sundial and astronomical tool.
And to anchor this structure globally, we have to talk about volume. While Giza is the tallest ancient pyramid, originally standing at 146.5 meters, it's actually not the largest by volume. That title belongs to the Great Pyramid of Cholula in Mexico. Cholula's base is 3 times larger than Giza's, covering an area literally equivalent to 9 Olympic-sized swimming pools. That really puts the scale into perspective, doesn't it?
Section 2. The ultimate math problem. Let's put on our project management hats to understand the severe logistical crisis faced by Khufu's lead architect, Himienu. This wasn't just about stacking stones, it was about managing extreme constraints.
Our first major constraint? Time. Based on the span of Khufu's reign, this massive construction project had a strict, non-negotiable timeline of roughly 20 to 23 years. Every single phase of construction, from quarrying to the final placement, had to fit within this tight window.
Constraint number 2 is material volume. They had to quarry, shape, transport, and perfectly align roughly 2.3 million massive stone blocks. We're talking over 6 million tons of total weight. And keep in mind, they were using copper tools and quartz abrasive to shape this stone, including raw granite brought down the Nile from quarries in Aswan, which is 800 kilometers away.
So here's where the math gets absolutely unforgiving. When you divide that staggering mass by a 20-year window, it demands a relentless material flow rate. They had to place 1 block every 2 to 3 minutes during daylight hours. That requires moving roughly 340 cubic meters of material every single day. You simply cannot achieve that rate without a flawlessly engineered transport and lifting system demanding tens of thousands of hands operating in perfect unison. Section 3. Evaluating the ramp models. Knowing from physical evidence at Karnak and texts like the Rhind mathematical papyrus that ancient engineers calculated ramp volumes to solve extreme bottlenecks, we really need to evaluate the competing structural hypotheses for how they actually moved these stones. The most common theory you'll hear is a single external long ramp. But as engineers, we immediately hit a wall here. To maintain a manageable 8% incline, which is roughly the maximum steepness workers could realistically drag a heavy sledge up, a single ramp reaching the pyramid's apex would need to be over a mile long. It would require more raw material than the pyramid itself. Plus, there just isn't enough physical space on the Giza Plateau to accommodate it without completely destroying the surrounding cemeteries and temples. Then there's another popular hypothesis, an external spiral ramp wrapping around the exterior faces. On paper, this kind of solves the material volume issue. as it uses the pyramid itself for support and stays nicely within the footprint of the plateau.
But as architects, analyzing the logic, we can quickly spot the fatal flaws. A spiral ramp completely obscures the corners and the outer casing. That ruins the engineer's ability to measure the precise angles needed to ensure all four edges meet perfectly at the top. On top of that, the narrow path heavily restricts the two-way sledge traffic. Remember our math? You absolutely cannot hit a 3-minute per block deadline if your transport teams are caught in a single-file traffic jam on a narrow ledge.
Section 4. The internal spiral solution. This brings us to a really revolutionary structural hypothesis proposed by French architect Jean-Pierre Houdin, which elegantly balances material scarcity with the need for rapid progress.
Houdin's model suggests a brilliant hybrid system. For the bottom third of the pyramid, where the vast majority of the volume is concentrated, a short external ramp was used. But once they hit about 160 feet in height, an internal spiral ramp with a 7% grade was simultaneously built inside the structure to finish the top 2/3. The external ramp was then dismantled, and its blocks were recycled to build the upper levels. This brilliantly explains how lead architect Himinu minimized both ramp materials and total manpower. To test this incredible theory, we look to the Scan Pyramids project. This is a modern archaeological initiative utilizing advanced, non-invasive digital tools. By using technologies like thermal imaging, mu-in radiography, and microgravimetry, scientists have been able to look inside the pyramid without moving a single stone. They've even recently confirmed the existence of a previously hidden corridor on the north face.
These diagnostics act as massive clues. A microgravimetric survey actually reveals a clear pattern of lower density spiraling along the very edges of the pyramid. This perfectly aligns with Houdin's internal ramp theory. Furthermore, researchers have identified L-shaped rooms at the corners. These open notches would have allowed workers to use simple wooden cranes to turn the massive blocks 90 degrees, keeping that constant upward flow of traffic moving smoothly. Section 5. The human infrastructure. Finally, let's step away from the stone itself and see how this builds into an understanding of the incredible human infrastructure that made the Great Pyramid possible. Because a structure like this isn't just an engineering marvel, it is a triumph of social organization. Excavations right within the Giza complex reveal massive, dedicated builders' quarters and adjacent cemeteries located right next to the pyramids. This definitively proves these builders were not disposable slaves. Being buried near the royal tombs was an immense honor, strictly reserved for respected, highly skilled professionals.
The archaeological finds from this workers' village detail a really well-managed daily reality. We're talking massive bakeries and breweries capable of feeding thousands. We see evidence of a high-protein diet, lots of cattle bones, proving these skilled laborers were regularly eating beef, which was a major delicacy in ancient Egypt. We even see advanced medical care. Skeletons show perfectly set broken limbs. This was a valued, cared-for workforce deployed in highly specialized teams, proving that human coordination was the true hidden architecture here.
Which leaves us with this final thought. Was the true wonder of the ancient world simply the geometric stacking of millions of stones? Or was it the unparalleled human organization, the logistical genius of Himenu, and the mathematical logic that allowed a society to achieve the absolute impossible? I'll leave you to ponder that.